This is EC 201, lecture 48. In the last class, we looked at how one might try and implement a second order low pass filter, and we saw that this is a band pass output. So this is the inverting band pass output. This is the non-inverting band pass output, and this is the inverting low pass output. And this particular choice of component values will result in a second order section with the following denominator: D of S, which is of the form S square by omega P square plus S by omega P QP plus 1, where omega P is simply given by 1 over RC, okay, and QP is Q. Alright? I have chosen both identical capacitors. Okay. Such a circuit which implements a second order denominator is often called a biquadratic section, or a biquad for short. Alright? You understand? And in general, if you want a completely arbitrary second order section, the general form is what you can have. You have the same denominator, alright, but the numerator in principle you would want to make it arbitrary. So you would want to be able to realize a numerator of the form K1 plus some K2 times S by omega P plus some K3 times S square by omega P square. This is the general form of a biquadratic section. Why do you think this is called a biquadratic section? Have you seen similar nomenclature before? What is something of this form called K1S plus K2 by K3S plus K4? Bilinear. It's a ratio of two equations, both of them correspond to a straight line. So this is a bilinear expression. By the same token, this character here is a so-called biquadratic expression, and an implementation which realizes this is basically called a biquadratic section. Now that we know how to realize this, based on this knowledge, can you tell me what I might be able to do to realize a general numerator of this form? What do we have? This basic biquadratic section that we have derived so far has got the following. What is the numerator here? Minus sum S by omega P times, actually there is omega P QP. The non-inverting band pass is of the form S by omega P QP by D of S. And what about this step? This is a constant, in this case happens to be minus 1 by D of S. Alright? You have these three guys with you. The question is, can you do something and realize an arbitrary numerator? Denominator of the transfer function we want is D of S. So it basically means that some linear combination of these transfer functions should be able to give us what we want. The only thing that we are missing in the numerator here is what? The S square term. So any suggestions on what I can do? You can represent the input as D of S by D of S, and this has got 1 plus S by omega P QP plus S square by omega P square. You understand? So a weighted combination of this guy, or the other chap, and this, you should be able to realize any arbitrary numerator. It's just a matter of adding this and this in the right proportion. Alright? So the general approach to realizing the numerator is to take the direct terms of V in, the band pass output, the low pass output, and you multiply them up by constants A1, A2 and A3 and add them up. And by now you know how I can do this using an op-amp. So I'm not going to go into the details, right? It's pretty trivial. And I should be able to realize arbitrary numerator by D of S. Does it make sense? And this also reinforces another concept that we have seen earlier. What did we see earlier? I mean, if you have a numerator that is a constant, all the zeros are at infinity. Okay. Now, if the coefficients of the numerator of the higher order terms of S in the numerator are not all zero, then the transfer function has got finite zeros. If there are multiple paths from the input to the output, we saw that you will get zeros, and this is just turning the same fact upside down. If you want zeros, you must have multiple paths from the input to the output. So there is a direct path from the input to the output, there is a path through the band pass node, and there is a path through the low pass node, and by varying the relative strengths of, or the relative weights with which you add these three quantities, you will be able to realize an arbitrary numerator. You understand? How sharp the filter transfer function can change as a function of frequency is determined by the order of the transfer function. So with the second order transfer function, you probably just got some kind of gentle roll off like this. If you wanted a sharper transition, you would have to increase the order. So it might be something like this, and as the order becomes higher and higher, this transition band will become narrower and narrower. And how would you recommend that I try and realize the high order transfer function? Pardon? So any higher order transfer function h of s can be broken up into a product of second order sections, and if you have odd order you have a first order section. And so on. So how would I realize this? I know how to realize this chap, and I know how to realize this and how to realize this. I know that because all of these are biquadratic sections. So if I wanted to realize the composite transfer function, what would I do? I can simply cascade these sections. Okay. Alright. So let me ask you a question. So this is a first order low pass filter, for argument's sake 1 ohm, 1 farad. So the transfer function is 1 over s plus 1. I can copy and paste. Now what happens if I cascade the two like this? What is the transfer function? 1 by 1 plus s the whole square. Hey, but I thought we all decided that you can cascade things, and you can only multiply transfer functions when the transfer functions are not altered because of loading. So 1 over 1 plus s the whole square is certainly not correct. You have to go and do the math, write Kirchhoff's equations, and okay. Or when we have the active filter that we just discussed, what do you think happens? Can I simply cascade? Can we cascade or can we not? If we can cascade, we are happy and done. If we cannot, then we will figure out what to do about this. For example, let's say we had an all pole fourth order filter. So let's say h of s, for example, was of the form 1 over d1 of s times d2 of s, where each of these guys are second order denominators. So as you said, I will realize 1 over d1 of s and 1 over d2 of s, and the question is, if I cascade the two, am I alright or is there a problem? You can cascade. Why? Okay, please note that the second order sections that we have derived so the ideal op amp is a voltage controlled voltage source. So the output impedance looking in at any of these terminals in principle is 0. The Z out here is 0, the Z out here is also 0, and the Z out here is also 0. So since the output impedance is 0, in principle they can go and drive any load, which means that if you cascade this with another second order section like this, then the composite transfer function will simply be the product of the individual transfer functions. That is unlike what you would expect with simply cascading a bunch of RC sections or a bunch of passive elements, because the output impedance is not zero, and the moment you tag something else along at the output of a passive network, you will find that the transfer function of the passive network itself is altered because of loading. Does that make sense? Okay, such filters are also called active RC filters, simply because it contains active elements R and C. Quite straightforward. Okay. So, given a transfer function, you should now be in a position where you will be able to implement any high order transfer function by simply breaking it up into second order sections. You know how to realize a second order section, and you can put all of them together, cascade them all, and you will be able to realize the transfer function that you want. Now, a couple of things that I want to point out with respect to op-amp circuits, and this also will carry over to feedback circuits in general. Let's first assume that we have an amplifier here. Let us say the output impedance of the op-amp is not zero. Okay, so there is finite gain, which is A, and a finite output impedance so op-amp gain is A, and the output impedance, let me call it RO. The question is, what would be the output impedance looking in here? First of all, what kind of control source is this? It is a voltage controlled voltage source. So ideally, if the op-amp is ideal, what should be the output impedance? Z out must be 0. Alright. Now, the question now is to sit and figure out what the output impedance in practice is. We have already seen that any op-amp that we design will definitely have finite gain, however large it might be, and we will have some finite output impedance. We put a common collector amplifier at the output to reduce the output impedance, but you know that if you burn a finite amount of current, the output impedance of a common collector amplifier is, it's 1 by Gn. Now how will I find the output impedance of this VCVS? The op-amp is not quite as ideal as we might want. So what will you do? You de-energize the independent source, alright, and then what would I want to do? Apply a voltage, measure the current. Okay. Apply a voltage, find what Ix flows. Now, if this is Vx, what is this voltage? Vx by K, alright. And what is this voltage now? Minus AVx by K, alright. And what is this current therefore? Vx plus AVx by K divided by RO, alright, plus this current here, which happens to be Vx by KR, is the total current flowing out, which means Vx times 1 over RO times 1 plus A by K plus 1 by KR must be Ix, which I can write as Vx by Ix, which is equal to the output impedance Z out, must be one over RO times 1 plus A by K plus 1 by KR. And what can you say about A by K in comparison to 1? So hopefully A by K is much larger than 1, which implies Z out is what? Approximately one over RO times A by K plus 1 over KR, and I will multiply the numerator and denominator by R naught times A by K R naught times K by A. So that will give me. Can you comment about this factor in relation to this? A will be very large and R naught is small to begin with. So you can approximate this as R naught into K by A. So the output impedance with feedback is R naught divided by A by K, okay, is approximately, because we have neglected one here and one there and so on, okay. And what is R naught? The output impedance of the powered amplifier without feedback. And what is A by K? It's the loop gain. The closed loop gain would be 1 over the feedback factor times loop gain by loop gain plus 1, and the loop gain is the gain, loosely speaking, the gain you get when you go around the loop. And if I cut the loop and go around, I will get, okay, approximately A by K. I say approximately because in reality there will be some effect of this R naught. If I break the loop, there will be some effect of R naught. But this is not a very rigorous discussion. But what I want to point out is that clearly the math is telling us that the moment you apply negative feedback around an amplifier with an output impedance R0, the output impedance of the feedback amplifier is reduced dramatically from the output impedance without feedback. So the question now is, why this makes sense? Why do you think this makes sense? What happens when I inject a current Ix into the amplifier? If the output impedance of the amplifier is 0, that is if R0 here was 0, then what do you think will happen when I pump a current into the amplifier? Yes, so what do you think will happen to the node potential of this amplifier here, Vx? If RO was 0 and if I pump the current Ix into the output of the amplifier, what do you think will happen? Let me back off. Ix was 0. What is Vx? What is Vx? 0. Is that clear to everybody? Now, if RO was 0, that is, you had no output impedance, and I pumped the current into Vx like this, what do you think would happen to Vx once I pumped in a current? It will remain 0. Why? Because this is a voltage source with 0 output impedance. So all this current Ix will simply flow into the amplifier A. The output impedance is 0, the voltage will not change. Correct? Now, let's go one more step forward. If this is R0, okay, and I didn't have this feedback loop, what do you think will happen to Vx when I pump in a current Ix? Vx will simply become Ix times R. Is that clear? Alright. Now, when I close the feedback loop, what do you think will happen? When you pump Ix into R0, the output Vx will tend to rise to Ix times R0. If the output goes to Ix times R0, what is the negative feedback loop attempting to do? It is trying to keep this node voltage equal to this node voltage. That's all the negative feedback loop is trying to do. Alright. So, when you pump in a current, momentarily the output will tend to go towards Ix times R0, which means the moment this voltage goes up, what do you think will happen to this voltage? This will also go up, though by a smaller value, but equal to Ix times R0 divided by K. Alright? So then what is the negative feedback loop doing? The negative feedback loop, all that it cares is that these two potentials must be the same. If the two are not the same, it will kick the output in such a manner as to try and make these two voltages the same. So, what do you think happens the moment this voltage goes up in this fashion? What is the negative feedback loop thinking? It's saying, oh my God, the output voltage is too high. I need to reduce it. So it goes and kicks this node so hard, it does whatever it takes to make this potential equal to this potential. So it's going to pull this node low, thereby pulling this node potential low. Does it make sense? So that means that if you inject a current Ix into this node Vx, it will not be Ix times R0, it will be much smaller. If I pump in a large current Ix and the output voltage doesn't change at all, it's equivalent to having a very low output impedance. From this discussion you can see, when you try to realize a VCVS, the output impedance reduced by a factor of the loop gain. Do you understand? Does this make sense? Let's consider what happens to the input impedance so let's say the op amp by some the amplifier is not as ideal as you would want, and there is some input impedance in the amplifier. Ideally, an op amp, as you have seen, okay, has got infinite input impedance, zero output impedance, infinite gain, and so on. And it's quite easily conceivable why the input impedance of an op amp might be finite. Do you think it will be finite when you have a MOS based op amp or when you have a bipolar transistor based op amp? Why? So beta is not infinity, so when you have a bipolar transistor based op amp, you end up with finite input impedance. So now let's see what happens to the input impedance once you apply feedback. For this discussion, let's just assume that the output impedance is 0. We just do one non-ideality at a time. The whole idea is, again I must confess that this is not a very rigorous way of doing it. Unfortunately, there is no time to sit and do this whole negative feedback loop gain rigorously as I did for the last set of students. I will just illustrate the basic idea with this op amp type circuits. So how would I figure out what the input impedance is? Apply a current, find the voltage, apply a voltage, find the current. So let me just apply a voltage here. If this is V out, this potential got to be I will write Kirchhoff's equations at current law at that node. Okay, so we can think of it as Vx Rn. Alright, and then I'll find the Thevenin equivalent of V out and this resistor divider. So that will be V out by K, and the output impedance of that, the Thevenin impedance is basically R parallel K minus 1 into R. And what is R parallel K minus 1 into R? Is equivalent to a single resistor of value R times K minus 1 by K. Is that clear? So this potential, that is that at the inverting terminal of the op amp, must be V out by K times Rin plus Vx times R times K minus 1 by K divided by Rin plus R times K minus 1 by K. That is the potential at that node. And what is V out? Vx minus this monster here. Let me call this Vy times A must be the output voltage, which means We're not really interested in V out as such. We are interested in Vx minus Vy by R. V out is nothing but Vx minus V out by K times Rn plus Vx times R by K minus 1 by K times Rn plus R times K minus 1 by K. We'll get to the intuition part as soon as we work out the maths. So, V out times 1 plus A Rn by K divided by Rn plus R times K minus 1 by K must be equal to A times Vx, or rather A Vx times 1 minus R times K minus 1 by K divided by Rn plus R times K minus 1 by K. Okay, I just may write this figure for the benefit of the backbenchers. How can I simplify this? Approximately equal to A is very large, okay, so you can neglect the 1 in comparison with A Rn by K divided by blah blah blah. So this is approximately equal to V out times A Rn by K divided by Rn plus R times K minus 1 by K. Alright, and this must be A Vx times Rn by Rn plus R times K minus 1 by K. So I should be able to cancel these two guys out, cancel this guy out, cancel Rn out, which means V out is approximately equal to K times Vx. Does that make sense? Alright. And all this whole thing is telling you, even if there is a finite input impedance, the output voltage remains pretty much K times Vx, K times the input voltage, as long as the gain A is large. But that's not what we were interested in finding. We wanted to find Vx minus Vy. Please note that V out is nothing but A times Vx minus Vy. Alright, and we were interested in finding Vx minus Vy by Rin is Ix, that's the current that flows in from the input, correct? Which means that the input impedance Zin is nothing but Vx divided by Ix, which is Vx minus Vy by Rn, and Vx minus Vy is nothing but V out by A and V out is nothing but KVx, which means Zin is approximately equal to A by K times Rn. Does it make sense? So what can you see? The input impedance with feedback is the loop gain times the input impedance without feedback. That's what the math is telling you. What is the intuition? When we have no feedback, it's straightforward. The input impedance will simply be Rn, because if I push in a current, the incremental, the voltage will be whatever current I push in times Rn. Fine. And when I yank this node up, what happens to this node potential? This also goes up, and if the gain is finite, we see that the difference between these two voltages required to maintain a finite output voltage is if there is some output voltage here, what must be the difference between the input of the amplifier to be able to maintain that output voltage? Very small, but by how small is very small? V out by A. This gain is A, guys. So if the output is V out, then the difference in the input potentials must be V out by A. So the current flowing through Rn must be V out divided by A divided by Rn. Or another way of looking at it is, if the difference between these two is very small, it's equivalent to say that if I yank this chap up, this potential will also go up by almost the same amount. If you yank one end of a resistor up and the other end of the resistor also moves up by almost the same amount, then the potential difference across Rn is very small. Okay, in the limit that A tends to infinity, the potential difference is actually 0. So if the potential difference across the two terminals of this resistor is almost 0, then the current flowing through the resistor is also almost 0, which means that if I yank this voltage up, Vx up, the current drawn from Vx is very small, which is equivalent to saying that the input impedance looking in is very large. Please note that it comes out of the math. That's not the point here. So you can see that as the loop gain tends to infinity, the behavior of the voltage controlled voltage source will approach that of an ideal VCVS, where the input impedance becomes infinite, the output impedance becomes 0, okay, and so on.